Is a lot of your people have eye defect, as you say. And okay, I know maybe the geographical
Yes,
location.
Julius,
Oh,
please turn off video. I don't think it's necessary.
Good afternoon to all. As today's speaker is Dr. Santosh Singh Rathore. Dr. Santosh Singh Rathore is currently working as an assistant professor with the Department of Computer Science and Engineering, Indian Institute of Information Technology and Management, Gwalior, India. He has received his PhD degree from IIT Roorkee, India in 2017 and MTech degree from IIITM Jabalpur. He has supervised 20 master's dissertations, about 30 undergraduate projects, and is currently supervising 7 master's students. He has authored more than 25 research papers in international and national journals and conferences, and has also authored or co-authored 2 books with Springer. His research interests are software fault prediction, software quality assurance, empirical software engineering, object-oriented software development, and object-oriented metrics. Dr. Rathore was the recipient of the SIGSE Travel Award 2012 and Genesis Award 2012 and others. Santosh sir, you can start now.
Thank you, Dr. Prabhas, for the introduction. So, I'll share my PPTs, and is it okay if I keep my video feed off? Because the bandwidth may be an issue, maybe an issue here. So, if it is needed, you let me know. I'll switch on my video camera also, right? Give me a moment just to see. This one is.
Yes, sir, is properly fitted.
Oh no, this is something else. Just give me a minute. This is something. Let me see. Browse from. Just a second. Okay,
Yes,
so
sir, it's properly visible, sir.
okay, right. So I'll continue. Wherever there is a problem, you simply interrupt me and let me know so that I can fix it, right?
Okay, sir.
Okay. So today, basically, for next 40-45 minutes, I am going to talk briefly about the topic which is feature selection, and the two techniques which people generally use in feature selection, these are the famous one is the PCA, which is principal component analysis, and earlier linear discriminant analysis. So uh, let's move towards the feature selection. So before discussing what a feature selection is, first we need to know what a feature is and why basically we are talking about this whole thing. So whenever we talk about any entity which we are interested in, let's say for a machine tool, and we want that entity, that machine should learn about that entity and all, we supposed to represent that entities based on some characteristics, and those characteristics are the features of that entity, that object, whatever you can call it. So that's why the feature are the core part of any machine learning or any AI model or technique, because if we are collecting the right set of features, then it means that we are representing the entity or object correctly. And if we have represented it correctly, then the machine, we can give the multiple instances of that to the machine, then machine can learn about them correctly also. So feature is a core part of any data, right? And we know that sorry. Okay, I think somebody talking. No. Okay, so the feature is that only it's the representation of something based on some characteristics, right? So whenever we want to collect information about the entity, we try to maximize that information, right? So we collect all the information. Uh, Somebody is raising the hand. Is there any issue? I don't know.
No, sir, you can continue.
Acha, okay. Right. So, so when we basically collect the information, we want to collect the maximum information about that object. So, obviously, we collect many features about that object or that entity, right? But when we uh, feed that input to the machine, sometime the thing is that that data which we have collected is not good enough so that machine can learn. So what machine to machine try to find out the patterns in the data, and if it can find out the good patterns, then it can easily discriminate among the different classes or different categories of that particular object or that particular data, right? So here the maybe the more is not a good thing, right? When we have many features, some of them are unnecessary, some of them are redundant, some of them are correlating with each other, so some a subset can be generated of them and all. So there are various regions uh, for which we want to do the selection of the features, right? So where feature selection is a process that chooses an optimal subset of features according to certain criteria. Now the thing is that whenever we are reducing the number of features, feature selection is obviously we are generating a subset which is lesser than the actual features. So think it that whenever we are selecting some features, we are losing some information about that object or something, right? Whatever feature we are removing, obviously that information characteristics also being removed. So idea here is that how we can select subset of features such that we can make sure that there is no loss of information, right? As well as uh, we are reducing those that set or coming up with a subset. That's what the feature selection is all about, right? So it says optimal subset of features, in a sense those features are perfectly fine for a machine to learn, as well as it's a subset, so that it's a something which is truncated or reduced from the original set, right? And we do so because to improve the performance, to the thing is that for the real world entities, the features can be many. There can be 10, 20, 50, 100, 200 features, and when features are increasing, the load on model is also increasing. Like the model cannot learn means fastly. The problem is that just I think some background noise is coming. No problem. So problem is that if we are having a large number of feature set, then machine may take hours to learn from it, which is also a degree which we cannot afford. So that's why we want to reduce it. Or there are other things also like dimension reduction and noise and all removal and all, which we will be seeing in the coming slides. Right. So feature selection, more or less, the aim of feature selection is this actually. So now when we talk about the methods of feature selection, there are two ways how we can select a feature. First thing is that we can assess capability, individual capability of each feature and see how much distinguishing power that feature is having, right? So if that feature is having a higher distinguished power, we keep it. If that feature is having a lower power, we remove it, right? But here we are treating each and every feature individually, and we are not looking among the interaction. Sorry, we are not looking interaction among the features. Fine. This is one thing which is also known as the univariate sort of feature selection or filter based of feature selection. Fine. This is the perfectly right. There is no problem with this thing, but the thing is that sometime a feature is a big feature, but when that feature is combined with another feature, their combination of both of them can have a more power than the individual of them, right? So univariate feature selection is fine, but that aspect we are missing. So that's why we also look for the we also supposed to look for the multivariate sort of feature selection where there are more than one features and their interaction we are also assessing. Wrapper based method comes under that category. We will be seeing them also. Then we have something known as the embedded methods also, which are inbuilt within the machine learning classifier. So I will be talking about some of these things before moving with the PCA and LD. Right. So filter based method selection, filter based method, as I told you, it's a univariate feature ranking method. So here, what we are doing basically, we are assessing the power of each and every feature individually, and we are generating a rank of them, right? The feature which has the higher distinguishing power is the top ranked. The next features is the slightly lower, then it goes like this. So it's a decreasing order sort of arrangement of the ranks, right? And then we can put a threshold. Let's say we only want to use the top 10 feature, or we want to use the top 20 feature, right? And we select, and that's a subset, or that's our subset actually. Okay, so filter based feature selection is performed at the time of pre-processing of data. That's why univariate feature selection or filter based method are the pre-processing step, which we do with the data before data is being exposed to the machine, right? Machine, we haven't given any input to the machine, but we are making data good. We are pre-processing it, right? Features are selected before using a tech algorithm, and it doesn't remove the multi-collinearity, which okay. So multi-collinearity says that how much correlated a feature is with another feature, right? If two features are highly correlated, that's a multi-collinearity scenario, right? So regression method like linear regression and all, they suffer from this problem. So if two features are correlated, ideally they both are representing the similar information. So we can select one of them and can remove the other. But since in the filter based method we are only thinking about, we are only assessing the individual capability, so there is no way we are assessing the multi-collinearity here, right? So this is the problem remains in with the filter based method. If somebody has any doubt, you can interrupt me anytime, right? Otherwise I'll continue with the lecture. So this diagram depicts that thing. We take set of all features, we select a best subset of them by doing the feature ranking and putting a threshold over them, and then finally they can be given to any machine learning algorithm, and then output can be generated. Here machine learning algorithm not playing any role in selecting the feature. it relies on general uniqueness of data, right? Uses the exact assessment criteria, which we will be seeing also, and then rank them and select the threshold. How many features we want to select? Top 10, top 50, top K, top N. That sometimes is not a fixed thing. That's something which is subjective sometimes. So we also need to know how much feature we want to select. Sometimes people use a criteria which is log n. So if there are n features, then log n features are selected in the subset, right? So these are the things people do. So some of the criteria through which we can rank the features. Information gain is one criteria. Chi-square test is another criteria. Correlation coefficient, variance threshold, mean absolute deviation, etc. So idea means there are various methods also. Idea is that we select a method which helps us in identifying the distinguished power of the feature. So information gain is one of the very famous thing which is there in the decision tree also. So I am just discussing briefly about this, and then other words in a similar way also, right? So sorry, yes. So let's say there are numeric features, sorry, x1, x2, x3, and xn, various. So we have numbered every feature with x1, x2, x3. They all are independent variable or columns in our Excel sheet or CSV file, right? And we try to determine the information gain of every feature, which is ig of x1, ig of x2, and all. And then we rank the feature in the descending order of their information gain, and then we put a threshold and select all which are above the threshold. So how we calculate the information gain? So information gain, sorry, one thing which is there in this information gain calculation is that it says data variables, sorry, variables having the categorical values, right? So if your data columns are not in the categorical, then you need to convert them, right? So continuous data must be converted to the categorical data. Only then this method can be applied. So it based on the idea. So information gain, basically gain of attribute A, GA, sorry, gain of A is equal to the information which is there in the data subtracted from the information which this individual feature is covering, right? So first we need to calculate the information of whole data, which is info D, and then we need to calculate the information which this attribute A is covering, and then we subtract both of them. That's a gain, information gain of that attribute, and we do same for all the attributes, and which one having the highest gain is ranked first. So information of whole data would be very simple. We will see an example of it also. It says that it's a summation of all the m examples pi log 2 of pi, right, where these are the positive and negatives value which we sorry, pi is the probability that attribute is belonging to that class ci, right? So pi is the probability it's belonging to a class, and there are multiple means, since we are doing the we have the categorical data, so there are classes, right? So when we see the data, this thing would be clear to you. Then information of that attribute A would be the dj divided by the mod of dj divided by the d, where this d is a, sorry, info, sorry, which is dj is, I think is not written here, but it's act as a bait for the jth partition. So dj by d, it acts as a bait, and then the information d is the average amount of information needed to identify class label in d. Okay. So but let's move to an example. These things would be clear there. So let's say we have a data where there is a feature age, there is a feature income, there is a feature student, and there is a feature credit rating, and the output which we want, which we are deciding is whether that person can buy a computer or not, right? And we need to see whether these all four feature are needed, or we can reduce some of them. So let's say we start by calculating the information of this age. So here first we need to see how many positive examples are there, how many negative examples are there. So let's say positives are yes and negatives are no. So by computer there are, if we look into this, then we can say no's are 1, 2, 3, 4, 5. There are 5 no's and there are 9 yes, because there are total 14 examples, out of which 5s are negative and 9s are positives. So information of this data would be info of D, which is 9, comma 5. So it says that minus, which is the probability pi, which is going to be 9 by 14 log 2 of 9 by 14 minus 5 by 14 log 2 of 5 by 14. So this simple calculation, if there are 3 classes, then 3 categories, sorry, then it can, there is another term also which can be added. It goes like this, and so it says ki information of this data D is 0.94, right? And then we need to do the same calculation for this age attribute. So for the age, can be less than 30, can be between 31 to 40, can be more than 40. In less than 30, there are 5 examples which belong to the less than 30, and out of 5, 2 are for the yes category, 3 are for the no category. Similarly, there are for the range 31 to 40, there are 4 examples, all are for yes only. For greater than 40, there are 5 examples, 3 are for yes, 2 are for no. So we can simply calculate uh, the information gain here. So for the first part, there are 5 examples, so 5 by 40, and then info of 2, 3, because 2 are positive, 3 are negative. And this 2, 3, I2, 3 would be open like this only, I9, 5, right? Similar calculation will go here. Same goes 4 by 40, I of 4, 0. It also it will also calculate it similarly, and same goes with the third term 5 by 40, I of 3, 2. So in this way, the information which this single age attribute is preserving is 0.694. So gain here is of 0.246. The same calculation would go for the income, would go for the student, and for the credit rating. And it says that ki out of all 4, the age is having the highest information gain here, 0.246. So this is the ranked one. Income, sorry, the student is ranked 2, credit rating is ranked 3, and income ranked 4. And then if you want to select top 2 or top 1 or top 3, you can simply select of them. So this is a simple criteria which we can use for the uh, which is information gain based, and through which we can rank the attributes, right? I'm not discussing, I mean, since the time is also limited, so we are not discussing much in detail, but you got the essence ki how can we basically rank the attributes. The second methods are basically the wrapper based. So the another problem with the filter based is that it not taking input and it not taking any feedback from the algorithm for which we are generating the subset, or we are doing the feature selection. So it assuming that it is selecting the universally best feature, which can be fed to any learning algorithm, and that learning algorithm will work fine, which may not be true in the real world scenario. So wrapper based method says that they say ki we have a set of all features, and then we generate a subset of features, but by taking the feedback from the learning algorithm, right? So it says ki we give a set of features, learning algorithm give the feedback, and based on that we keep on adding or dropping some features, and finally we will be having a best subset generated, and for which the model will be trained finally. So how it can be done, we see it, but here idea is that the features subset which we are selecting is not universally good, but it is good for that learning algorithm only. So if we are changing the learning algorithm, we also need to redo this whole exercise. That's why this is not a pre-processing step as per se, but it is something which we are doing along with the training of the model. So here we tries to train the model with a reduced subset of features in iterative way. So how this algorithm works? The idea here is that okay, so this theory is fine. We iteratively going through the features, and then we having a stopping criteria. Once that criteria reaches, we say, okay, this is the best subset which we can go through. But how can we, how we supposed to iterate and how we supposed to stop? That is something we need to decide. So there are three ways. Through, there are four though, but famous are two only. Others are just combination of it. So forward selection says what? We means if we have n features, we initially pick one of them, right? And we feed that feature to the machine learning algorithm and see how much performance that machine learning algorithm is producing, right? We record it. Then we select another feature, and then we supply feature first and feature 2 both together to the algorithm and see when we are adding another feature 2 to the algorithm whether is algorithm performance improving or not. If it is improving, then we keep both of them, feature 1 and feature 2, right? And otherwise, if algorithm performance is not increasing or even decreasing, then we simply remove the feature 2 because we get to know that feature 2, adding feature 2 not helping us at all. Then we select another feature 3, and then we analyze it with already selected subset. Let's say if we have selected previously 1 and 2 both, then we supply 1, 2 and 3 now, all 3, and see how algorithm is performing. If algorithm is performing better, then we keep it, otherwise we remove it. And we keep on doing it for all the features, right? So in this way, all the features which when we have added them not helped in increasing the performance of the algorithm, we remove them simply, and all other we keep, and this is our subset. Fine. So in this way we are analyzing the interaction among the features also, and we are selecting a subset based on the algorithm. This method is fine, but there is only a single drawback of this feature is that, let's say we decided to use 1 with the 2, and we found that feature 2 is not performing good with feature 1, so simply removed it. But what about the scenario where feature 2 can work good with feature 3 or feature 4 or feature 5? But because we simply discarded it, we are not considering it again. So here thing is that we haven't tried all the combinations. That's the problem. So, but exhaustive search is also not a feasible thing for us. If there are 5 features and trying all the combination and permutation is not feasible, right? Because that search space would grow very large. So the another solution is the backward selection. So backward selection says what? We start with the all features, right? We start with the okay. Let me show you with the images. I forget to change this slide. So this feature forward feature selection is fine. So for the backward, what we do, we start with all the features, right? And we train the model and see how much performance model is giving. And then we randomly remove one of the features and see by removing that feature whether performance has decreased or increased or remain same only. If it has increased or remains same, then we we remove that feature, otherwise we again add it and then we remove another feature. So what we are doing here, we are doing a reverse analysis where we see when we remove a feature from the set, how it is impacting the learning algorithm's performance. If it is not impacting at all, right, or even it is improving, then obviously that feature is a bad feature and we need to remove it. And we keep on doing it for all the features till we have a subset where all the features means if we remove any one of them, then machine learning algorithm performance would be decreasing, which we don't want. So it's from the figure also it's seen, we start with all the features, we remove one, and then we see how it is impacting, then we remove another and see how it is impacting and all. So here since we are starting with the whole features and then removing some of them, so we are not missing the part where the interaction of a feature with other features hasn't been considered, right? We have here all the features, or sorry, all the interaction had been considered. So backward elimination is a bit better than the forward selection in that sense. Okay, so these two things people generally use. Then bidirectional and random generator is fine. So bidirectional says ki we start one cycle of forward selection and one cycle of backward elimination. And so it says ki begin search in both the direction, forward selection, backward elimination. Be stop when one search finds the best subset, or when searches reaches to the middle, right? When we remain with this, let's say 5 features in both the directions, so we stop at that criteria. Random generation says ki we randomly we doing everything random, means we are randomly removing something and see how it is impacting. If it is not, so means it's a random removal of features and see how it is impacting, and if it is impacting, then we add it or drop it. We do follow those things, right? So these are the some ways, means these are the two ways, filter and wrappers, through which we can select the feature subset. Embedded methods are simple ones. So embedded methods are what? They say ki feature selection is a part of the algorithm only, right? So like a decision tree. So decision tree is a embedded method where feature selection we are doing. So means when we are selecting a root node. So root node is the best node, obviously. Then all the nodes at the label 1 are the second best. Then all the nodes are the third level, at the third level are the third best. It goes like this. So these are the embedded methods which combine the quality of filter and wrapper within. Linear regression with forward selection, backward elimination is another example of embedded method, right? So they already have that thing with them. So I am moving forward with the other aspects. If anybody having any doubt, you can interrupt me and ask, right? Otherwise, I am continuing with the things. So principal component analysis is another way to reduce the dimensionality of feature. So till that point, whether it's a filter based or it's a wrapper based, we are removing some features, right? And then we are saying ki, these are and we are remaining with a subset of features. PCA and LDA, they work slightly different. They don't generate a subset of feature. They basically generate a different representations of feature, sorry, with the condition that that newly transformed features are not correlated to each other and they have a better discrimination power. Like so, a PCA do what? It basically generate a linearly separable representation of features which can be used for model training. So how this thing works and what is the theory behind it, I'll discuss it, right? So just a second. So dimensionality reduction is not as same as the feature selection. So dimensionality here, dimensionality is the number of features or number of columns in a simple sense. So there are means we are not eliminating any feature, whereas we are extracting the features or we are transforming the feature to something new. So in a sense, ideally, if we are not losing any information of data, whereas we are increasing the discrimination power of the data. But here also we drop some principal components. So that's another aspect of it. So feature elimination disadvantage, you gain no information from the variable that you have dropped, whereas feature extraction says ki you can create new independent feature where each independent variable is a combination of the old one and it has a better discrimination power. Another thing which is there about this PCA is that PCA is an unsupervised feature selection technique or dimensionality reduction technique, better word would be. and LDA is a supervised dimensionality reduction technique. So for the PCA, we don't require the dependent variable column at all, right? Because it is simply transforming the independent variable to something new. Whereas LDA, it's but similar to the PCA, but it requires the dependent variable information also. That's a fundamental difference between these two terms. So right, so dimension reduction, there are various reasons for that. Better linearly separable data, the transform data would not having any noise, right? It's better to visualize and all, because it has a linear, sorry, they are linearly separable or orthogonal to each other. So something about the PCA dimension reduction technique. It is used to reduce the dimensionality of a larger data set by performing a set of variable by transforming set of variables to a smaller one. It transforms some large number of variable into the smaller one, which we call the principal components. We will be seeing them, right? And it captures the data information which is there. So idea is pretty simple: reduce the number of variable of a data set while preserving the as much information as possible, and each new variable after PCA is independent to each everyone. So here a principal component is nothing but a vector. Like a component is nothing but just a vector which basically representing something about the data. So the principal component one, it assumes the first principal component is capturing the maximum amount of information. Then the second principal component supposed to be the 90 degree or 90 degree or the orthogonal to the first one. So it is completely separable from the previous one, and it must be covering something new. So all principal components, they start at the origin of the axis, and the first PC is the direction of maximum variance, and then subsequent PC or principal components are having the other variance. So variance means the first principal component is covering the maximum information about the data, then the next one, then the next one is goes like this. So ideally, theoretically, the number of principal components are equal to the number of features. So if there are originally 10 features, then it will generate 10 principal components. But since we have seen the first principal component is covering maximum variance, second is covering the second maximum variance, goes like this. So obviously we can select, let's say, top 5, and then top 5 are basically having the maximum of information. So some tail principal components can be removed. And how we can remove it? There is one thing which is known as the variance preserve. So let's say if we decide each principal component will answer how much variance it is preserving. And let's say if you want to say I want to preserve 95% of variance of data, then it means that if first principal component is preserving 50%, second is preserving 30%, then first two preserving 70%, then we keep on adding, and once we reach a point of 95, let's say first 6 principal component when added all together covering 95% of variance, then we continue with those 6 only and remove all other. Right, so this is how things work. So we see through an example also how it is done and all. So this is all theory about this principal component. So it starts with the thing which is the standardization of data. So whatever data values you are having, you supposed to transform them in a such a way that the mean of that column is 0 and variance of that column is 1. That is known as the standardization of data. There is a for filter or formula standardized which easily do for us, right? So we transform all the features in this way, where mean of every feature is 0 and variance is 1. Then we compute something which is known as the covariance matrix. How we will do it, we'll see. So covariance matrix we compute of the data, and then so it's going to be a matrix, a square matrix. Covariance matrix is a square matrix, and we know from the algebra point of view for a matrix we can easily derive the eigenvalue and eigenvectors. So we calculate the eigenvalue and eigenvector, whereas eigenvector is a direction of that principal component, and eigenvalue is that how much information it is, magnitude of that vector. Sorry, if we simply say, so eigenvalue and eigenvector are representing the direction and the magnitude of that principal component, right? Then we sort all of them based on the in the decreasing order of their eigenvalues, uh, and then we select the top k eigenvalues, and then we generate something known as the projection matrix W from this eigenvector. So the eigenvector that we have generated, we multiply them with the original data, and that would be our transform data. Okay, so we transform the original data set X via W to obtain the this feature subset by. So projection matrix will be multiplied with the X original matrix, and that would be our new transform matrix. So if we see here, standardization is pretty simple. Right. Then we generate something which is known as the covariance matrix. Covariance matrix, if there are X and Y two features, then covariance of X with X, covariance of X with Y, sorry, X, Y, Z, covariance of X with Z. Then covariance of Y with X, covariance of Y with Y, covariance of Y with Z goes like this. So it's a diagonal matrix, means diagonal diagonal every it's a covariance of X with X, and then X covariance of X with Y or covariance of Y with X is same, right? Ideally same values होंगी, तो how covariance can be calculated? Covariance of X and Y is like a mean value of X, which we are subtracting from the individual value, right? Xi is the individual value and X is a mean of that column. Similarly, by I is the individual value, by bar is a mean of that column. We multiply both of them together and then sum all those values and then divide by the total number of values in that attribute minus 1, n minus 1. Okay, so this will be a covariance between X and Y, and it goes similarly for other thing. And then sign is basically something. So if a sign is negative, then if sign is positive, then two variables are increasing or decreasing together. If it is negative, then they are inversely correlated, right? Either correlated positively or inversely correlated. So if there is a data value X and data value Y, X having some numbers, Y having some numbers, right? So first thing, we will be calculating the covariance of it. So let's say covariance matrix is like this, 0.6165 and some number 0.6154. So covariance of X with Y or Y with X is same. So that's why these diagonal values are same. And then covariance of Y with Y, which is 0.716. Then we calculate its eigenvalue and eigenvector. So eigenvectors for two eigenvectors are equal to the number of the size of क्या बोलते हैं, if there are two variables, two eigenvectors would be there, three variables, three eigenvector would be there, goes like this. Eigenvalues, for each eigenvector there is one eigenvalue. So for this eigenvectors, the first one is the first row, second one is second row, and eigenvalues are this. So then we sort both according to their eigenvalue, the eigenvectors. How much we need, we can simply sort them. So then we calculate the eigenvalue and eigenvector. This is plot only, so this is nothing, same only. So we select, either we can keep all of them or we can select some of them, and then we multiply that with the original matrix, and then this would give us the transformed one. Okay, so इसमें here the row feature vector is a matrix with eigenvector in the column transpose, so that the eigenvector now the row. So we transform the matrix and then we multiply it with try. So this is how PCA works. And I quickly, because time is also running out, so I quickly go discuss the idea of LDA also. So and then there is an example also which can be referred. So LDA works similar to the PCA, So in PCA, what we are doing, we are generating a covariance matrix, and that covariance matrix is then we are using for the eigenvalue and eigenvector calculation. Linear discrimination analysis generate that covariance matrix differently. That's the only difference. Once that matrix is generated, all the calculations are same only for PCA and LDA. So the PCA is a unsupervised one, which is not taking care of anything about the output variable, whereas LDA do. So okay, so in PCA, the main idea is to re-express the variable to extract the relevant information by reducing the redundancy. We don't care about the feature for whether they are for they have a more discrimination power for a class, they have a less discrimination power for another class and on. So LDA says ki we calculate two things: within class variance and between class variance, right? And then we calculate, and within this within class or between class variance then help us to generate matrix which is between class matrix and within class matrix, and then these two matrix would be multiplied together to generate the matrix which is similar to the covariance matrix. So this thing may not be very visual to you. I'll try to zoom it. Right. I don't know how to zoom it. Sorry. Okay, no problem. I'll discuss with the in terms of algorithm. So this algorithm says what? I think all of you can see it. So it says that we have a data X which having some features, right? And means there are m features and we having n samples. So we have a n samples, each of which having the m features, and there can be, let's say, some classes of it. Let's say 2 class, 3 class. It belongs to 1 class or 2 class, right? Right. So it says that first we compute the mean of each class. Let's say out of n, some are belonging to the class A, some are belonging to class B. So we calculate the mean for each class, which is mu. So if there are 3 classes, so mu1, mu2, mu3, and then we compute the total mean, which is mu. And then we generate something which is known as the between class matrix by simply having this formula, which is mu I, which is mean of individual class I subtracted from the overall mean of the data, and then multiplied with the similar thing which is transposed, right? And this we do for all I equal to 1 to C, means all the classes which are from 1 to C, varying from 1 to C. This is SB. Similarly, we calculate the something which is known as the SW within class. So here mu I is the mu J is the mean value of a class J, which is varying from 1 to C, and we are subtracting it from for the individual feature like I varying from 1 to Nj, which where Xij represents the ith sample in the jth class. Okay. We are multiplying it with the transport of the same term, which is SW. Then we generate something which is known as the W, which is the multiplication of SB with the inverse of the SW. Okay. So this term W is generated, and as soon as this W is generated, after that all the steps are similar to the PCA. So now we calculate the eigenvalue and eigenvector of this W, and then we sort those eigenvectors in the ascending value of the eigenvalues, and then we select first k of them and then multiply them with the original data, and that would be our transform data. So here it says that we have the original data matrix X. So here W1, W2, W3 are 3 classes, let's say, and for W1 class, let's say feature are from X1 to Xn1. Then for W2 feature are from Xn plus 1 to Xn Xn1 plus N2, and for W3 features are varying from Xn1 plus N2 plus 1 till Xn. Right. So this is N into M matrix, which we generate something, a projection, which we multiply with this, and that would be our data after the transformation. So the this new data obviously will be similar means it will be having all the features put it in a linear equation, but they are linearly separable, and then we select some top of them. So this is the algorithm which I have discussed. The calculations goes like this. So there is, let's say, data, there are total 10 samples. We have two different classes, W1 having the 5 samples, W2 having the 6 samples. Total there are 11. For the class 1 there are 5 samples, for class 2 there are 6 samples, right? So we will be calculating the mean of first column, mean of second column for W1. mu1 क्या हो गया, तो ये average हो गया all these 5 values which is 3, average of these 5 values which is 3.6. Similarly, the mu2 which is mean of this 6 value and these 6 values. Then mu would be, which we have seen from this formula, mu would be the mean of all data, right? इस पूरे data का mean निकाल लीजिए, mu, and then the SB would be generated, SB1, SB2 would be generated, SB1 for the 1, SB2 for the second class, and then they both are summed together for the SB generation. Okay. SB equal to SB1 plus SB2. Similarly, we will be generating the SW1, SW2, and then summing both of them together for SW, and then taking its inverse, which is SW inverse, right? And then we simply multiply this SW inverse with the SB for the W generation, which is coming to 1.36 minus 1.31 minus 1.48, 1.42. And then we calculate the eigenvalue of it, eigenvector of it, and then we generate a projection matrix which is similar to the PCA. We multiply it with the original values like this, the vector which we have selected here, right, 0.69, 0.68 or something. Sorry, 0.68 and 0.74. This vector is multiplied with it. This is the transform data. The same we will be doing for the another class. And this is the transform data. The first one is here, the second one is here, and that is which we are using. Right, so this is all about the PCA and LDA. So I stop here because there is supposed to be some time for the questioning answering also. So I'll stop and would like to hear from the audience if they have any questions. Right.
I think there are no questions.
Okay, no problem. So I think I'll stop at this point.
Yeah, thank you, sir. Madam, ma'am. Sir, you can stop now.
Okay, fine. Sorry. Right. Okay. Okay, so I should sign out, is it?
Yes, sir, you can.